Welcome again to this massive open online course on advanced analytical technique, and we were studying the HPLC, and now we are on the last week of this course. And in the previous lectures we have discussed the various components of HPLC, and now comes the main component, that is the heart of HPLC. So let us explore the role of column in HPLC, that is the high performance liquid chromatography. So the significance of column in HPLC is the same as that in the GC. That is, it is a column where actually the separation of different components of the sample occurs, and the efficiency of any separation depends upon the efficiency of the column. That is, if the columns are efficient, then overall we get a very good separation. And the column in HPLC contains, as usual, the stationary phase, which is usually packed in a column, and the column in HPLC is generally made up of material of having high tensile strength. Sometimes we also use glass column, particularly the fused silica glass we generally use. These columns contain as many as theoretical plate as possible, keeping in mind that the run time will not exceed too much. So this column is actually maybe regarded as the place where the actual separation occurs. The efficiency of any column actually determines the efficiency of the separation of that particular sample. Generally, it is made up of some strong tensile strength material, generally stainless steel, and sometimes we also have glass column that are generally made up of fused silica glass. And as we know that the number of theoretical plates which are purely imaginary in nature, there is actually, in fact, there is no plate existing in the column, but still this is a concept given by Martin Sinch about the theoretical plates. So as many as theoretical plate, greater the number of theoretical plate, better will be the efficiency of column. So typically the size, the length of the column in HPLC varies somewhere between 150 to 250 millimeter, with an internal diameter ranging up to 4.6 millimeter. So this sometimes this length actually may be varied. Similarly, the internal diameter can also be varied depending upon the type of separation which is required. Okay, so let us move forward. That generally, as I have told you, that this material by which we construct our column should be of high tensile strength, so that it can withstand large amount of pressure generally required in HPLC. Sometimes, sometimes we actually apply 15,000 psi pressure. So the need is that the material should be strong, and generally stainless steel columns are used. Similarly, sometimes we also use the glass column, the fused silica glass. Sometimes we also use PEEK, that is poly ether ketone. These are tremendous material, very fine quality tubings, polymer based tubings, of course, which are very, you can say they are very stable thermally. They are very stable. They have very good internal diameter, so that your mobile phase flows uninterrupted. At the same time, they are chemically resistant also, so that they are, they give good performance. So that is PEEK, that is polyether ether ketone. Similarly, we have silica based packings which are generally used. It may be, it may also have the ability to, we can actually change the polarity of these silica based packings, which we are going to see in the coming slides. Similarly, we have polymeric packings for ion exchange chromatography. Sometimes we also use polymeric packings in the reverse phase HPLC also. So what I have said, that silica surfaces are usually considered because you can actually tailor their properties. You can actually induce certain groups, so that you can actually induce polarity. We have already seen in the previous slide that by just changing the methyl group by phenyl group, we have changed it to a little polar so that it can have good interaction with the polar solute molecules. So we can actually, by using silica, we can actually modulate the polarity of that particular stationary phase. Then comes that there are different type of columns. For example, the main column where actually the separation occurs is the analytical column. Generally, we use some guard column. These guard columns are generally placed before the main column so that the impurities cannot reach the main column. That is, this guard column actually acts as a protective column. That is, so that impurities, various suspended particles, various particulates can be filtered before entering into the main column in order to avoid clogging, in order to have good performance or good separation efficiency. Similarly, we have preparative columns. These preparative columns are used for large scale separations. They have very good sample bearing capacity. Similarly, in HPLC, we use capillary columns that are very small. They have very small diameter, but at the same time they have very good resolution. So we have to choose the column according to our need, according to the can say that what type of resolution is needed, and always resolution must always be greater than 1.5. how much sample is actually we need to separate. So all these factors should be taken into account before taking up or before deciding any column. Then comes the stationary phase characteristics. Of course, the stationary phase is very important, or you can say that it is the most important because it is the stationary phase on which the different solutes of the sample actually interact. And on the basis of interaction, they have different migration rates. And on the basis of different migration rates, they have different elution patterns. Or you can say they elute at different times because of the different migration rates. So particle size is very important. Smaller the particle size, compact will be the packing, and higher will be the efficiency of that particular column. Similarly, the pore size, it also affects the molecular axis, and we have seen the effect of pore size when we were discussing about the Van Demeter equation. So the pore size should be small. If we are using HPLC, then it should be lie between 2 to 4 micrometer, and we have also seen that in UHPLC this size should be always be less than 2 micrometer. Similarly, surface area. So greater the surface area, better the retention capacity. We have already discussed this. Now comes the chemical modification. For example, if we have these are the non-polar stationary phases. Now, if you have a solute, for example, which you want to separate, then you can change the polarity by inducing phenyl group, which is less polar. You can induce certain groups which are electronegative in nature, so that the stationary phase becomes more polar. So depending upon the requirement, you actually change the stationary phase. So generally, we prefer 3 to 5 micrometer particles for better efficiency and in order to have a good pressure. Because if the particle size is more, then we have to apply a large pressure so that our solute or our mobile phase along with solute can pass through the column. So we have to keep this in mind. Okay. Then comes the column efficiency. This is our old age equation which we have discussed many times. So the efficiency can be regarded in terms of the number of theoretical plates, which is given by 16 into TR upon W. TR is actually the retention time of that particular solute. W is the baseline width of that particular peak. So in order to have good efficiency of any column, we must have large number, or you can say as many number of plates, theoretical plates as possible. And this N, actually we have already discussed, it gets influenced by the particle size, the flow rate, okay, the flow rate which was actually we use optimum flow rate. Similarly, the column length, greater with the length, greater will be the number of theoretical plate, but at the same time we have to keep an eye on the time required for separation. So if you take long column, then okay, efficiency would be good, but the time of run also gets increased. So you have to keep an eye that what are the factors, what are the dominant factors, and what are the conditions which you have to satisfy for a particular separation. Similar temperature, we also have seen the effect of temperature. Temperature clearly affects the viscosity, and actually it affects the overall efficiency. And we have also seen, while we were discussing about the illusion chromatography, the programmed temperature or the programmed temperature separation. So column maintenance. Now it is very important to have a good efficient column, and for efficiently working of any column, regular maintenance is required. So we have to carry the regular maintenance, that is, we have to flush our mobile phase regularly on a regular basis, and we have to avoid air bubbles, because we have seen that air bubbles have created issues, and the peaks were distorted. Similarly, we have to use guard column. These guard columns are placed before the main column, and the main aspect of using these guard column, as the name suggests, these are the guards of the main column, because these columns actually filter the impurities. It filters the various suspended solids, particulate matters, various impurities, so that your main column can have a long, efficient life, working life. So sometimes when you have your peak shape distorts, that is a time when you have to replace it. So for example, in the reverse phase HPLC columns that are used for checking the drug purity, we have to keep it on regular maintenance. Okay, and these are the you can say these are the do's for doing the regular maintenance of our column. What are detectors? Actually, detectors are again have the same significance. These may again are regarded as the eyes of HPLC, the same analogy which we have used while we were discussing about the gas chromatography. So the role of detector is very important. In fact, detectors are the component of HPLC which gives you an idea about the start of a separation, about the end of the separation, about the elution of a particular analyte. So these detectors are sensitive with regard to change in concentration, with regard to change in any physical property or chemical property, whether it may be refractive index, whether it may be absorbance. Similarly, they are also sensitive to change in mass, and we have seen it while we were discussing about the GCMS detector. So the key requirement of a detector remains the same as for GC. So always detector should have high sensitivity, or you can say sensitive as like that of the GC. Similarly, they must be very good response. They must have very good response, and they should have stable baseline. That is, there must be no noise. Okay, the noise should not be there. Otherwise, sometimes it becomes difficult to separate the noise from the actual analyte which is being separated from the column, from the HPLC. Similarly, they should have a good linear range, and we have seen that the FID was having a very good range. Sometimes it ranges up to 10 raised to the power 7, from 10 raised to the power 3 to 10 raised to the power 7. Similarly, the FID was also having a sensitivity of 10 raised to the power 15 gram of solute per gram of the substance. So classification of detectors. Now here, detectors can be classified into two broad categories, namely the bulk property detector and the solute property detector. Actually, this bulk property detector compares the mobile phase alone with the mobile phase mixed with your solute, and it gives you an idea about the change in the property, any physical property. For example, a change in the refractive index. It is also sensitive with respect to the change in the mobile phase. So bulk property detectors are sometimes also called as the universal detectors. They may be also be regarded as universal detector. Universal detectors. Similarly, the second type is the solute property detector, or you can say specific property detector, because they are concerned, they are responsive to a change in particular property. For example, the change in the UV absorbance. For example, the change in some refractive index. So they are concerned with the change in a particular physical or chemical property, and they do not have any effect on the change of the mobile phase. So they are very good. These are very good for doing some gradient chromatography, these solute property detectors. And we are going to study the different detectors which comes under these two classes in the coming slides. So absorbance or UV visible detector. Of course, these UV visible detectors are based on the Beer-Lambert law, that is A is equal to epsilon Cl. Epsilon is the permittivity constant, C is actually the concentration, and L is the length of the cuvette. So these these absorbance detector may be of 2 or 3 types. That is, those which work on a fixed wavelength, that is called as a fixed wavelength detector. Those detector which can work on variable wavelength are called as the variable wavelength detectors. Similarly, we have a diode array detector, that are called as DAD detector, and they are they are versatile. They can measure a lot of compounds, because they actually based on the change in the UV absorbance. Okay, so this is a good aspect, but at the same time, because they work on the UV visible absorbance, change in absorbance, so sometimes there are compounds which are UV silent. So those compounds cannot be detected by using the UV visible detector. These detectors are very good for the analysis of the drug assays, as well as for the analysis of the phenolic compounds, because these phenols, some of the phenols absorb in the UV range, while some phenols are also having color, so they can be detected in the visible range also. So they are very good for detection of the colored complexes also. Similarly, we have diode array detector. They work in a full range of a spectrum, okay, and they are also used to detect the purity of any sample, these diode array detectors, and they actually detect the coeluting compounds, which is actually a problem when we were discussing the GC. So by using the diode array detectors, we can detect closely related compounds which have very less boiling point also. So they are very good for detecting impurities, for detecting any you can say any compound which is not advisable, or for example in pharmaceutical analysis they are very good. So they are very good for detecting those compound which has a fluorophore, or which is having some tagged fluorophore unit. So the principle is, that is, those molecules which absorb UV light emit fluorescence, and any substance which emits fluorescence can be detected by using these fluorescence detectors. They are again very specific, they are sensitive, and you can measure up to femtogram, that is minus 15 grams. So this is very sensitive. Again, these are only good for those compound which have a fluorophore in there, because they only respond to those compounds which have which only give fluorescence. Sometimes what we do, we use some tagged fluorophore unit, so that the whole compounds fluoresces. Similarly, this is also good for detecting amino acids, polyaromatic hydrocarbons, and other for example in butyric acids, where we have very good conjugation. Now comes the refractive detectors. Again, they comes under the bulk detector, and they detect the small changes in the refractive index between the mobile phase alone and the mobile phase mixed with the analyte. So these are universal detectors. They can be used for detecting an array of compounds. They are not suitable for gradient one, and they are less sensitive, but they are very good for detecting sugars, polymers and lipids. Now the hidden fact is that they need temperature control so that the baseline can be stabilized. This one, okay. Now there comes the electrochemical detector or ECD. The principle is again they are based on the redox principle. They measures the change in the oxidation or reduction current. So here we can have sometimes we can have a 3-component 3 electrode systems, and now sometimes we have 4 electrode systems where one electrode is working electrode, reference electrode and auxiliary electrode. So these are actually very good for detecting those compounds where there is a change of, or you can say where there is a transfer of electron. So they are extremely sensitive for redox active compounds, for neurotransmitters, for the detection of vitamins, phenols. And here the important aspect is that your mobile phase must be electrochemically clean. That is, it should not have any sort of agent which is redox active. So it should be redox insensitive, your mobile phase, okay. So other detectors, we have some specific detectors like the conductivity detector, which is very good for detecting the ionic compounds, for example AgCl, or example any other compound which is purely ionic. Similarly, we have ELSD type of printer, that is detector, that is called as the evaporative light scattering detector for non-volatile analytes, okay. Similarly, we have the mass spectrometric detector, LCMS. It is one of the most used detector in HPLC, and the beauty against that, it gives you about an idea about the identification, the nature of different analytes present, and also it gives about the structural identity of different components present in your sample. So it is very good because it gives you structural identification also. So nowadays these LCMS are used for biology people for doing proteomics or for detecting various metabolites. Okay, now it's a comparative table of various detectors which we have just read. So each one have certain positivity and certain at certain point we have to compromise. For example, the UV detector, its sensitivity is very high, selectivity is medium. We have to compromise at gradient use. Yes, we can use it in the gradient chromatography, and it is very good for detecting the various components of drug and also the impurities present in the drug. Similarly, we have diode array detector. The sensitivity is very high, selectivity is very good, gradient use, yes, of course, and application to detect impurities. Again, fluorescence detector, very high sensitivity, selectivity is also very high, gradient use very good, and it is very good for detecting the biomolecules. But at the same time, if your compound does not have any fluorophore, then you cannot detect it using a fluorescence detector. Similarly, we have RI detector, which is a refractive index based detector. Again, sensitivity is low. That is the bad thing. Again, selectivity is also low. It is not used for gradient, and it is good for detecting sugar. But at the same time, it is suitable for detecting normal, or you can say the routine compounds, and it is very easy to handle also. Similarly, we have electrochemical detectors. Again, the sensitivity is high, selectivity is also good, gradient use, yes, of course, we can change the polarity of our you can say mobile phase here, and the good thing is that they are redox active. But at the same time, if your substance is not redox active, then you cannot detect it using electrochemical detector. Now there are certain advantages, certain limitations. For example, UV detector is versatile, fluorescence detector is ultra sensitive, your refractive index is universal, you can detect a large number of compound. Electrochemical detector was specific. So the RI was very good. It is universal detector, but you cannot undergo you cannot actually run the gradient type of mobile phase where you keep on changing the polarity of the mobile phase for better resolution. So again, fluorescence is very good, but it is limited to certain compounds. Only those compounds which have a fluorophore. So let us see some of the examples. For example, in the pharmaceutical industry, for checking the drug purity and the different analytes, we actually combine two detectors, that is the UV detector and the diode array detector. The same thing which we have used in GCMS, that is we are actually using it a hyphenated. These are called as the hyphenated detector. Similarly, sometimes we combine the LC and EC, that is electrochemical detectors, and for detecting sugars, RI is the detector of choice. Okay, that is the refractive index detector. Now for doing for environmental analysis, generally for the detection of pesticides, fungicides, which actually contains aromatic rings, so fluorescence detector comes for our help, because most of these contain aromatic rings, and that is actually a fluorophore. Similarly, if there are certain metal ions involved, then of course they can also be detected by using the electrochemical detector. So these are some specific you can say applications for some specific detectors. Again, for food industry, to detect the presence of sugars, carbohydrates, we use the refractive index detector. For vitamins, for you can say proteins, we use these electrochemical detectors because there is a charge difference. Okay, so similarly in proteins, similarly in amino acids, we can use the EC detector. Now for the biochemical analysis, for proteins, amino acids, we can do the fluorescence, and the fluorescence detector is good for the detection of these type of compounds. For neurotransmitters, we can always use the electrochemical detectors which have very good sensitivity. Now the modern innovation, that is the microfluidic LC systems. These are very miniature type of liquid chromatographic systems. You can say that laboratory on a chip like type of system. That is, you use very small chip and you can resolve very small samples, and you can get a very big beautiful detection by using these miniature type of microfluidic liquid chromatographic system. Similarly, if you couple this system with MS, then you can also get the structural information of unknown compounds if present. Similarly, you can use the ICP-MS, that is the inductively coupled plasma, with the mass spectrometer. When you couple it, then you also get the information about the particular, you can say a particular ion or particular peak. So again, if you use the machine learning, then you can actually do detector optimization, that these programs can do your work very simple. Similarly, sometimes you have to use 2 or 3 detectors in a series so that you can have a very specific and comprehensive analysis of your unknown compounds present in the sample also as well.